Thank you very much. It's a great honor to be here and to speak about, basically it will be about results of Sinai and his contributions in mathematical physics related to mathematics and to physics. And I specifically selected this topic because I think that Grisha reflected on ergodic theory part of Sinai's work, and Doma will probably speak more on dynamical systems. So although part of the results, a big part of Sinai's contributions in dynamical systems can be considered as mathematical physics as well, I concentrate on other aspects of it. And this, between mathematics and physics, it was basically about what Sinai did from 70s upwards. Sinai himself yesterday said that it was a very important period when mathematicians started to study physics and go into physics and take problems from physics. And you know, this cat and dogs thing about mathematics and physics, it's a very interesting issue. And of course, mathematics and physics came from the same origin, and maybe it's difficult to say Newton was physicist or mathematician, but then separation or divorce happened. And in different times, in different countries, relations were different. It looks like in, say, in Germany in 20s, or in beginning of the 20th century, it was one community. And maybe in Europe in general, for example, Poincaré has written recommendation letters for Einstein, famously. And it's very interesting letters to read. And say, Einstein gave talks at the seminar of Hilbert. And in fact, Hilbert found so immediately that the equations are not symmetric the way they're supposed to be, and even wrote a paper about that. So it was a related community somehow. But maybe later, mathematicians started to talk less with physicists. Maybe they had enough of their own problems to concentrate to work on it. So it's an interesting relationship. And say, even Soviet Union, again, it was not maybe much contacts, although we can, there's a famous contact between Kolmogorov and Landau during the Second World War. Both were in Kazan, they were evacuated from Moscow, and Kolmogorov was working on turbulence problem, which was actually physics, it was not mathematics. Equations were not solved to discuss it. It was a very beautiful theoretical physics work, and they were discussing it, and they had different points of view. But it probably was an isolated episode. And this collective movement, which happened among many of great Russian mathematicians of a younger generation in the 60s, was a very interesting phenomenon. A very distinguished group moved towards physics and getting problems from physics. And this is Sinai, this is Dobrushin, Minlos, Berezin, Novikov from completely different origin, but also moving in the same direction, Manin. So I think the source was that it was a realization that interesting mathematical problems and were coming from physics, that this is a source of natural problems, interesting, challenging, and that's the direction to go. Probably it's an indication of certain stagnation in mathematics at that period. And then maybe nowadays, maybe more physicists going in direction in mathematics rather than mathematicians to physicists. So it's kind of a two-way street now. And it's very good. It's just indicated both sides need each other and they need to be in coordination. Maybe there is also danger when they come too close together, when physicists would kind of lose sense of theories should be confirmed by experiment or some measurements, so mathematicians would lose sense of proving things. But the advantages, I think, they overcome disadvantages. So it was an important movement, and I will discuss part of it. So I would list main contributions of Sinai, of mathematical physics contributions of Sinai. So he started to work on statistical mechanics in late 60s and worked through the 70s. I would say mostly equilibrium, but also non-equilibrium statistical mechanics. And the main contributions is Pirogov-Sinai theory and renormalization theory for hierarchical, Dyson's hierarchical models. This is joined with Pavlik Blecher. Of course, Pirogov-Sinai theory joined with Pirogov. Those were really fundamental things. It was many others, but I just choose the main things. It's really difficult to be selective. And so the next one was more or less the same time in the 70s, Schrödinger operator with quasi-periodic potential, spectral properties, with Dinaburg, with Yefim Dinaburg. This was very pioneering work, and I will discuss it probably during the talk. And then Sinai later on came back to the problem of spectral property of Schrödinger operator late in 80s, where he studied completely different case. There is kind of dichotomy between continuous spectrum, absolutely continuous spectrum, and pure point spectrum, kind of Anderson localization. So that is two different streams of work, continued in 80s. Sinai's random walk in random environments. One-dimensional beautiful work on random walk in random environment. New phenomena was studied and discovered there. It's easy to discuss. And I hope to have time. I'm not sure I will have time. Render-Burgers equation, what some people call turbulence. It's not just turbulence, it's Burgers, because Burgers equation is, also it looks similar to Navier-Stokes. It is not Navier-Stokes equation, and dynamics is quite different. This is joint work with Sven and myself and Alec Mazel. And turbulence itself, proper turbulence, random Navier-Stokes systems with Sven and Jonathan Mattingly, blow-ups for complex 3D Navier-Stokes systems with Dong Li. So that's kind of a list which I wrote, but it's not everything. I mean, there is a lot of things beyond this list, but that's the main thing. Now, I have a very ambitious plan to discuss statistical mechanics, Schrödinger operator, and Sinai's random walk. I don't think I will have time, but that's how it stands at the moment. That's my plan. And let's see how it goes. So I'm moving in direction of statistical mechanics. Now, so it happened in 60s, at the end of 60s, when a large group of mathematicians in Russia and in the West started to develop new science, rigorous statistical mechanics, in close contact with physics problems. Now, I think it was realization that at that time, a big part of probability theory was theory of independent or weakly dependent random variables, also Markov processes. And then it was realization that new type of problems, probabilistic problems, and most interesting problems coming from statistical mechanics. So that was kind of feeling which appeared simultaneously in the West and in Russia among this group of people. I think that Berezin and Minlos were the first who moved in this direction, and then they kind of brought to the same direction. They kind of convinced Dobrush and Sinai, they moved to the same thing. Dobrush and Sinai was both students of Kolmogorov. So I think that Berezin was not very long in statistical mechanics. He wrote maybe 1 or 2 papers, but Dobrush and Sinai stayed for a very long time, and they wrote classical papers. Now, the famous seminar on statistical mechanics in the 70s in Moscow was chaired by Minlos, Dobrush and Sinai, and Malyshev. So all 4 here. And that was a real interesting thing, because this seminar where the science was basically created, one of the main seminars. So there were no books, apart from a real book on statistical mechanics rigorous results. So this was created during these seminars, and they were incredible place of concentration of people and their efforts and the enjoyment and excitement. Now later on, it was Sukhov student of Sukhov, Gurevich, Pirogov, Schlossman, and many others. Now, this list is not extensive in anything. I mean, definitely many people should be included there. But just Oscar Lanford, Leibovitz, Lee, Bruel, Glim, Jaff, Eisenman, Galavoti, Fröhlich, Simon Spencer, and so on and so forth. So that's people who worked in this area. Now, this is a portrait of Kolmogorov. Sinai showed 3 portraits of Kolmogorov because he made many contributions. I show 1 because he didn't write a single paper on statistical mechanics. And this is a very interesting topic. Why Kolmogorov, who was a founder, one of the founders of probability theory, and his work was all around statistical mechanics, entropy, turbulence theory, which is part of statistical physics. He never wrote a paper on statistical mechanics. Although 2 of his students, Dobrush and Sinai, became very important in this subject. And I don't know the answer to this question. Actually, I was not the first who posed this question. I remember it was posed by Kozlov during the centennial conference of Kolmogorov in Moscow. It's an interesting question, and I'm not going to discuss this a lot. Just a remark that it was not alien idea at the time, because Hinchin, who was also very prominent in probability theory, wrote a book about mathematical methods of statistical mechanics and quantum field theory, maybe. It was in 30s, I believe, this book. So the idea was not alien, but still Kolmogorov didn't work on this. Right, now let's go to mathematics. So this will be crash course in statistical mechanics. Now those who want to take it for credit can come after the lecture to me, and we'll discuss the exam and other things. For others, I will just try to explain the main concepts. And so the basic notion is Gibbs distribution. So we discuss what is called spin system. Spin system on the lattice ZD. There is a very simple object. At every point I, point of ZD, there is a element of finite set. So plus or minus 1, the typical example. This is what is called Ising model, because Ising was German. Let's say Ising, not Ising. There are different pronunciations. So in this case, finite sets consist of plus and minus 1. It can be different finite set. This is the simplest setting. Just spin takes finite number of values. And so the Hamiltonian is a basic notion. So this is a Hamiltonian quasic model. So sigma is a configuration of all the spin on a lattice. And this is a formal sum. It's not a number. It is sum over all these brackets stand for nearest neighbors on a lattice. So you take any two nearest neighbors, and you multiply spin in these two nearest neighbors. That gives you a number. You take sum of them. It's infinite sum. That is a formal expression. Now, in general, Hamiltonian will be more complicated. It can't be any more complicated. You just have to figure out some pattern, maybe 3 spins, thing like that, and take sum over all lattice position of this pattern. So it's similar expression, but more general than that. Let's stay with Ising as a model, as example for Hamiltonian, but think about expression which is summation over all the lattice of certain pattern, of certain function depending on values of spins. All right, so next what you can do with this Hamiltonian, you can take what is called V. V is a volume. You take finite set on a lattice, cut certain set, and consider configuration of spin inside this set and outside. Outside will be sigma bar, inside will be sigma. So just two configurations we fix. Actually, better to say the fixed configuration of this sigma bar, because this is a boundary condition. You fix boundary condition, then you can define probability distribution for spins inside, for fixed configuration of spins outside. This is given by Gibbs formula. So you first define what does it mean, energy of interaction of spin. Oh, this V should be capital V here. This is a misprint. So this energy of interaction of spins inside the V with themselves and with spins outside. So this is sum over all nearest neighbors where both belongs to V, minus sum of sigma I, sigma bar J, where I and J are still nearest neighbors, one inside V, inside is outside. So it's just spins, you are ignoring interaction outside of V at all, but V with outside you put together. So this is an energy of interaction. And then you can write the Gibbs formula, and this is a basic formula. It's probability distribution of sigma V under condition of sigma bar is fixed. And it's given by exponentiating of this minus beta. Since I said that in statistical mechanics you always have minus and minus. So minus beta H, and 1 over Z, just normalization factor, just to make that this is probability distribution, that sum of all these probabilities is equal to 1. So this factor Z is called partition function, and there's a positive parameter beta, which is called inverse temperature. So this beta is 1 over kT, T is the temperature, this is inverse temperature. So it's one parameter family of problem. I should have put here beta as a parameter, but formula would look a little bit more complicated. So for fixed beta, this is a probability distribution. Now what we have is a set of all possible expression probability distribution like this, which is parameterized by V. You can choose any finite set V, and you can choose any boundary condition. So you look at this as a set of prescribed conditional probability distribution. So that's different from classical probability theory, where you consider finite dimensional distributions and they determine the field. Here you determine conditional distribution, and that's the setting of statistical mechanics. For giving set of conditional distributions, the question is, and that is called Dobrushin-Lanford condition. The question is Gibbs state, its basic definition, is a probability distribution on spin configuration such that conditional distribution for all finite subsets V are given by the Gibbs formula above. You can express it as the integral expression in easier way, but that's the way. So that's a basic definition which makes statistical mechanics part of probability theory. And then the question will be to describe these Gibbs states and to see their structure, especially when parameter beta changes from 0 to infinity. Because when beta is equal to 0, it's quite simple. There is no interaction. So all spin have this, they're independent random variables. This trivial thing, there is only one Gibbs state. Now, what happens with small beta and for large beta, that will be the topic of our discussion. So the main problem is to describe the set of Gibbs states as parameter beta changes from 0 to infinity. So what is a phase transition? There are different definitions of what is phase transition. Basically, it's singularities of partition function. For me, it would be the following thing. there exists more than one Gibbs state. If this set of conditional probability distribution is consistent with at least two Gibbs states, then we have a phase transition. If it's unique Gibbs state, it's simplification, but it's good enough for the discussion today. So the set of Gibbs states form a convex set. That's a very simple statement. So every convex set has extremal points. So extremal points are most important. If you know extremal points, you know the whole set, and they're called pure phases, this extreme point. So the task is to describe the extremal states, pure phases. Now, there is a general fact, which is non-trivial, well, which is very simple, actually. It's a kind of Markov theory. No phase transition in one-dimensional case. So if dimension of lattice is 1, for all beta, there is only one Gibbs state. Again, it's not always true, but for systems, I consider it is true. If finite range system, it's correct. And basically, that is because the process is Markov process. So that is a simple statement. Now, the next statement is less simple. It says the following. It's high temperature regime. When beta is small, which means the temperature is high, then spin variables, they're not exactly independent, as what beta is, but they're weakly dependent. And there's a perturbation theory which makes use of this. And this is called Kirchhoff-Salzburg correlation equation. This is non-trivial, but it tells you that it allows you to prove that Gibbs state exists, unique, and analytically dependent parameter beta as long as beta is small. That is well understood part of high should be written different. And so that is well known, but it's already non-trivial. And then the next thing which I want to explain, and that's very simple again, there's one fact that how you can construct Gibbs states. Existence of Gibbs states is a very simple fact. So you take increasing volumes Vn, sequence of volumes that get bigger and bigger, covering the whole lattice, and then any sequence basically of boundary conditions, sigma and bar, and they take any limit point for this process. So it defines the probability distribution with increasing sets of spins. So take limit point, not necessarily even limit. Now the space is compact space of measures on this compact, the set is compact, we have finite number of spins, so the limit points always exist. That will be a Gibbs state. Question is whether limit exists, and whether you can have different things by choosing different boundary conditions. But any limit point of such process will be a pure phase. All right. So we already understand what happened with small beta. Nothing interesting. Well, there's unique Gibbs state. What happened for large beta? So for large beta, the Gibbs probability distribution concentrates on figurations with small minimal energy, because it's e to the minus beta. So when beta takes large, you want h to be very small. Then it will give dominant contribution to e to the minus beta h. So this configuration of small or minimal energy, they called ground states. So basically, you want to understand what are the ground states, configuration of spins of minimal energy. Now, what is a minimal energy? You can ask because it's a formal sum. Definition is very simple. If you have infinite configuration of spin, it's called a ground state if the following is correct. If you change the spin configuration in finite number of places, then the difference in energy is well defined, and it must be positive. So you cannot decrease energy by changing finite number of spins. You can do it by changing infinite, but not finite number. Okay, so we are considering it's an important remark, we are considering translation invariant of periodic Hamiltonian. So if we consider spin here and there, they interact the same way, or there is a periodic configuration. So because of that, we're interested in translation invariant or periodic ground states as well. So spin configurations should be either translation invariant or periodic. And for Ising model, of course, there are just two ground states, all pluses or all minuses. It's ferromagnetic Ising model. So this is two periodic, in fact, translation invariant configuration, they are ground states. But for more complicated Hamiltonian, it can be finite number, it can be different number of ground states. Now, consider, as I said, huge volume V, but finite volume with some boundary condition, with giving by one of the ground states. Say, for Ising model, it will be either plus or minus. And the main question, will a typical configuration inside V look like a ground state, typical with respect of Gibbs measure, or it will forget about boundary condition? By typical, I mean typical with respect of Gibbs formula distribution. So that's what I'm saying. Huge V, W is a finite thing. It's not going to infinity. So you fix boundary condition, and then you see what will be probability distribution of spins inside W. And you want to say whether will it fill the boundary condition, or when V increases, the influence will be weaker and weaker, and you will not feel it anymore. So if you feel it, it's called, you have phase transitions, long-range order, you are in a good, I mean, you can prove interesting phenomena, presence of phase transition. If you don't, then there is no phase transition, then everything is relatively simple. So does probability distribution depend on sigma asymptotically? If it does, then Gibbs state is, if it doesn't, then Gibbs state is unique. If it does, there is a phase transition, the system exhibits the long-range order. We shall see that there is a Isaac, in the Isaac case, it's the case. Now let's consider Isaac model. So I put plus boundary condition a boundary, and then there is a typical some configuration of spins inside. Now it's difficult to deal with combinatorics of these spins because there are two complicated things, right, going on. How you handle it. So the basic idea goes back to Peirce, is the following one. You introduce geometrical object. You introduce separation boundary between pluses and minuses, these red curves. They called contours. So for every configuration, there is a set of contours. They separate pluses of minuses. If you know boundary condition as set of contours, you can reconstruct the configuration. So you can either speak of configuration of spins inside or configuration of contours. It's up to you. But of course, it's geometrical object. It's much easier to deal with it. And also notice that whenever you have a boundary, this contour gamma, then you lose in energy because instead of plus in your minus in your Hamiltonian, if you have plus and plus here, say if you have plus and plus here, you have minus term in Hamiltonian, this will give you plus. So you lose 2 units of your energy whenever you have a boundary. Because of that, it's very easy to prove the following formula, that this is not a probability, it's correlation function. So what is the probability of those configurations which are consistent with certain gamma? So if you take any gamma on a lattice, on a dual lattice, how many configurations which are consistent with this gamma? That is a correlation function of this contour gamma, and it's easy to show that this probability is less or equal than e to the minus 2 beta gamma. Look at this beta, this will play an important role here. Gamma is the length of this contour, or it will be volume on a higher dimensions. All right, now we're interested what will happen with a spin at point at the origin when V is large. So what is the probability that this spin is equal to +1, and what is probability is equal to -1? If both probabilities tends to 1/2, then probably you don't have phase transition. But if this probability of having plus stay above 1/2, bounded away from 1/2 when V increases, then there is a phase transition. So that's what you want to study. What is the probability of having minus here, -1? So what does it mean that there is a -1? It means that there is at least one contour which separates boundary from the origin, because minus should be separated from pluses. You have pluses everywhere on the boundary, you should have this contour. Okay, the problem is then to estimate the probability of having a contour surrounding the origin, any contour. Now you can say, okay, I'll consider contour of length n. N is minimal length of contour is 4, so it will be sum from n to infinity. Now you have e to the minus 2 beta n, because this is an energy, this is a probability of contour of length n. It is less than that number, times the number of contours of length n surrounding the origin. Now this is a combinatorial number which is easy to estimate. When you do contour, you can go up, you can go to the left, to the right. There are 3 possibilities when you can continue your contour. You cannot go the way you came. So there are 3 to the n possibilities for you to go for every choice of your length of a contour. And also the starting point of contour, it's easy to see that it's bounded by 1/8 of n squared, because it's just, you cannot start very far away from the origin and surround it. So it's very easy to estimate. You look, this is an estimate for this probability. Now, of course, if beta large enough, this is a finite sum, because this term will dominate that term. So if beta is larger than logarithm 3/2, then this is a convergent sum. Moreover, it tends to 0 when beta goes to infinity. So what it means is that for any alpha less than 1/2, there exists beta naught such that this probability will be less than alpha, less than 1/2, uniformly in V. The same inequality holds in a limit V goes to infinity for the plus phase. Sorry, for the plus phase, I mean for the minus phase. The same inequality holds for the whole plus phase when you go to the limit. And by the symmetry, similar inequality holds for the probability of sigma 0 equal to +1 in the minus phase. So you construct two phases. Plus phase, where probability to have plus is greater than 1/2, minus phase, where probability is less than 1/2. So at least two different phases, you have phase transition. So that is what is called Peir's argument, and it was well known, and this was a very beautiful contribution of Peir's to this subject. Now, what is Pirogov-Sinai theory? Pirogov-Sinai theory is a far-reaching method which allows to study Gibbs state, construct phase diagrams for general spin system in the low temperature regime. Finite number of spin variables, but taking finite number of values, but general system. So you consider any periodic Hamiltonian with finite range of interaction, like Ising model, and a finite number of periodic ground states, which satisfy the Peir's stability condition. I'm not going to say what is Peir's stability condition. It's a very natural condition, which is very easy to verify for concrete models. So this is very constructive conditions, and denote by R the number of different ground states. Now, you have to consider R-1 parameter family of Hamiltonians, which is perturbation of original Hamiltonian. So R is the same R as here. So instead of Hamiltonian H0, you have to consider H mu, which is perturbation. And mu is just mu1, mu r minus 1. And they also finite range periodic Hamiltonian. So they can be considered as external fields perturbing H0. So it is assumed that, and that's a very important assumption, that H1, HR minus 1 resolve the degeneracy of the ground state. So what it means is that when you change mu1, mu r minus 1, for resulting Hamiltonian, you can get any subset of these R ground states. So this R ground state only for this Hamiltonian. But when you perturb, you maybe would have all but one and all but two. So any choice or any subset of this R ground state can be realized for particular choice of parameter mu1, mu r minus 1. So that's condition on this Hamiltonian, which means that they are kind of linearly independent. Again, easily verifying condition, because this is condition for beta equal to infinity. It's just condition for ground states. And now, suppose the condition of the previous side is satisfied, then for beta large enough, the phase diagrams is small perturbation of ground states of the ground states phase diagram. So what it means, there exists a point mu beta such that this system with this, if you fix beta and take mu on beta, system has R pure phases, the same as ground states. There are R curves which starts at that point for which you have all ground states except one. And then you have codimension 2, you have surfaces 2-dimensional where you have all curves, all ground states but 2. And then the full stratification, so on up to full stratification. The whole thing you can construct. And this will be just for some nonlinear choice of this mu beta and those curves. So let me draw the picture here. So for Ising model, it's kind of slightly different because of the symmetry. So for Ising model, the perturbation would be this external field, sum of the spins times mu. And then these two lines, gamma 1 and gamma 2, will be just mu less than 0 and mu greater than 0. Mu and beta is identical 0 because of symmetry. But if you break symmetry, you will not have this beautiful behavior. And so that's a typical diagram for, say, 3 ground states. So on level of ground state, at point mu equal to 0, you have 3 ground states. Here you have just 2, second and third. Here you have 2, 1 and second. And here you have 2, 1 and 3. In between, you have only ground state which is not 1 and only 2. So 3 here, 1 here, and 2 there. So that is a picture for beta equal to infinity or t equal to 0. Now when we perturb it, you consider large beta, mu moves to point nearby, mu on beta, and then you have this curved gamma 1, gamma 2, gamma 3, which are perturbation of this gamma 1, gamma 2, gamma 3. So here you have 2 ground states, 2 phases, 2 phases, 2 phases. Here is 1 phase, 1 phase, 1 phase. So that is the most you can do for low temperature regime, and that is done by very complicated control. So this is a far-reaching generalization of contours, and it's a very complicated technique, probability perturbation technique apply, but you get as good results as you want. So basically it closes the subject. And after that paper, basically, it was a good understanding of low temperature regime and high temperature regime. I would say there are two general methods, basically, Pirogov-Sinai method and reflection positivity to study phase transitions for such systems. And Pirogov-Sinai theory was extended in the case of continuous spin by Dobrushin Zagradnik, and that was done later. But as I said, this theory basically is a settled thing. So I would not say that it was much of development later because the problem basically was solved. I would say that I know the story that I think Ruel had a prize attached to this problem, which was well-known problem for everybody. And he said that he would bring beautiful bottle of champagne, and he brought it to the conference in Repino, and this champagne was gladly consumed during this conference by the participants when the result was announced. This is Sergei Pirogov. I'm sorry, it's not a very good picture, but that's what I got on the internet. And this is Pirogov from Pirogov-Sinai theory. Now, I would start about Schrödinger operator. I will see how far I can go. So Schrödinger operator is a completely different subject. The paper was published more or less at the same time. And I would say that in this middle 70s, 74, 75, 76, all three papers appeared. Pirogov-Sinai theory, Schrödinger operator, absolute continuous spectrum with Dinaburg, and Blecher-Sinai on renormalization theory. So it was a very grand period. And in general, in dynamical system as well, Feigenbaum was at the same time his papers on period doubling, Michel Herman, his global results. So it was a very exciting period. Anyway, so Sinai has written two seminal papers on this subject, one in 74, joined with Dinaburg, regarding the existence of absolute continuous spectrum, and another in 87, dealing with pure point spectrum. So in the first paper, he considered continuous time, continuous Schrödinger operator, that's classical Schrödinger operator with potential V on X, which was quasi-periodic. But in second paper, it was discrete setting, and it's slightly easier to discuss discrete setting. So I'll consider this operator. So it's discrete Laplacian if I add two psi fn, but two of psi are kind of incorporated in this term. And this is a self-adjoint operator which acts on Hilbert's operator L2 on Z. So the question is to study the spectrum of this operator as a function of parameter lambda, which is a coupling constant in front of the interaction, potential V, as a function of theta and a function of alpha. The most interesting case of alpha is being irrational. Now when alpha is, Sinai considered the case of large energies for this equation, and this is equivalent to considering, so what it means large energy, it means that this term, Laplacian, dominates the potential, because large energy comes from Laplacian. And so it's equivalent in this setting to consider small values of lambda. So basically, the result is that for small values of lambda, there is an absolute continuous spectrum. Maybe not only absolute continuous, but there is an absolute continuous spectrum. And there are extended eigenfunctions of continuous spectrum, like Bloch wave function in this problem. That was the main result of Sinai-Dinaburg. I will formulate it later. But the main novelty was that they introduced the methods of KM theory to this subject. So the method to prove the difficult thing here is small devices. And to deal with this problem, they introduced KM methods. Now, potential V on X is a smooth function on a unit circle. The main example is V on X is equal to cosine 2 pi x. This is most studied example, and I'll have time to present some results about it. In this case, basically now almost everything is known about this almost Messier operator. And you'll see how far the subject moved from that time. In this case, the operator is of course almost Messier operator. So if alpha is a rational number, then this is a periodic operator, not quasi-periodic. And the spectrum is absolutely continuous, with spectral bands separated by gaps. It's well-known classical result by Floquet theory and Bloch. Bloch waves, it's a wave to construct these eigenfunctions of continuous spectrum. So Sinai and Dinaburg have introduced Kolmogorov technique to the area. They proved that in the case of rational Diophantine alpha, you have to consider typical alpha, Diophantine. For small lambda, there exists a set of energies E of positive measure corresponding to Bloch waves of the form of quasi-periodic functions time exponent, which satisfy the equation that Hamiltonian times this acting on this function. So it's eigenfunction of continuous spectrum. This statement implies the existence of absolute continuous spectrum. The main problem is related to small devices. Now, I like this picture very much. I call it Sinai and KM. This is picture of 63. So where is Sinai? Yes. And this is also Sinai. And this is Arnold. Now, this is Moscow State University. So Kolmogorov is someone there. Because he worked there and he also lived there. His apartment was inside this huge building. So with probability close to 1, he's inside. So where is Moser? Moser is taking the picture. So it's picture taken by Moser. So it's definitely Sinai surrounded by KM. And what I like in this picture that they look so happy both. And so it probably brings a lot of fun to do mathematics. It's for young people who are taking exam. Now, let me just say a few words about Schrödinger Cocycle. This would explain what it means. So we want to solve this eigenvalue problem, right, for this equation. Take E. We don't know E. But let's take any E. And let's solve this equation. Then we can say, what would we psi n plus 1? You can express it through psi n. If you look at it, basically you take pair psi n plus 1 psi n, and there is a matrix. If you multiply psi n minus 1 on this matrix, you get new pair. So basically how you solve this second order equation. You start with initial data at 2 points, and then multiply on matrices. So if I denote this matrix by SE theta, which is SL2R matrix, then what we have that psi n minus 1 is equal to product of these matrices times psi 0 psi minus 1. So we have initial data and multiply by those matrices. Now what is the structure of these matrices? These matrices depend on point on a circle. And basically, my next slide shows what we have here. So we have a circle. At every point of a circle, there is a matrix. And then we have translation of circle by angle alpha. And we take product of those matrices along trajectory of rotation. This structure is called Cocycle. When you take product of matrices along transformation T, which is supposed to be ergodic mostly. So this rotation by rational angle, it's not very stochastic, but it's ergodic transformation, not mixing. And so it's enough to discuss Cocycle and its statistical properties. So basically, you have to take product along this thing. Now, in fact, you should look at it slightly differently. There is a fiber structure. So there is a plane living, which kind of parameterized by any theta. So over every theta, there is a fiber, which is two-dimensional plane. And this matrix, in fact, is a linear operator, which transformation from R2 here to R2 there. So when you take product of the matrices, you take linear transformation from this one to resulting one. Why I'm saying that is that then you can ask the following question. Suppose I change the variable at every of these fibers, but I make change of variables depending on theta. Theta depending change of variables at every of this plane. So I have family of matrices B depending on theta, which are non-degenerate matrices with change of variables. Then, instead of this cocycle, I'll have conjugated cocycle in new variables. So this new cocycle will be B theta times old cocycle times this, sorry, this is not A, this would be SE, SE times B minus 1. So that is a conjugated cocycle, the new cocycle which you get. And now the task is to find change of variable in such a way that this would be much simpler than that one. What is simple? We say cocycle is reducible if one can find a smooth family of non-degenerate matrices in such a way that this new cocycle is a constant cocycle. It doesn't depend on theta. Then you're in a good shape. And to do this linearization or reducibility, you need to use KM theory. So KM method allows to prove that in this case, a small gamma lambda, the cocycle is reducible for positive measure of energies E, and this implies existence of absolute continuous spectrum, and that is the Dinaburg-Sinai theorem. Now later, Håkan Eliasson showed that reducibility holds for almost all E, which proves that the spectrum is purely absolutely continuous in the case of small lambda. So there is no other part of spectrum. There is no eigenvalues with decreasing with L2 eigenfunctions. And that's later result of Eliasson. Now, to prove, what about poor point spectrum? To prove that, now the task is different. It's like in statistical mechanics. Low beta, small beta, large beta. Here, small lambda, large lambda. So for large lambda, you want to prove that potential dominates, they play more important role than the Laplacian. So to prove that for large lambda the Pareto has pure point spectrum, one has to construct a basis of eigenfunctions in this space L2, which are L2 functions. In fact, they are going to be exponentially decaying, like Anderson localization. And this was done by Sinai and by Froelich, Spencer, and Witwer, which independently did the same thing. Actually, it looked like 3 years, but in fact, it was maybe less years between the work done. Sinai proved that for Diophantine alpha and typical theta, the spectrum is pure point, provided that lambda is large. Moreover, corresponding function decay exponentially fast, Anderson localization. Anderson localization was in case of random Schrödinger equation. So this is more settled part of Anderson localization theory. And the proof is very involved and is based on difficult analysis of resonances. So I'm citing here, this citation is of Michael Goldstein. He cites Sinai saying that localization is a game of resonances. And in fact, the method of proof is based on very careful analysis of resonances in this problem. I don't have time to go into it. I just maybe want to say what does it mean from Cocycle point of view. So that is about this oscillated maybe stable and unstable directions, which I discussed. So we have this cocycle with a product of these matrices along the trajectory, right? And we know that if we applied it to this thing, for large lambda, this cocycle would have one unstable and one stable Lyapunov exponent. So what it means is that there is a direction, and a unique direction such that if you apply these matrices, this will tend to 0 exponentially fast. That's fine. So there is 1, phi 0, phi minus 1. Now, but you also want this to decay in another direction. So it means that there is another vector such that you apply this backward operator. It also goes exponentially fast in other direction. Now, unfortunately, these two vectors would be different. But if you find E in a special way, then for special values of E, they would coincide. And when they coincide, then you will have exponentially decaying eigenfunction. And that's how you can think about it. Unfortunately, the proof doesn't go this way. But give you some intuition. By changing parameter, you can maybe sometime attain that this unit vector and this unit vector coincide. But again, you have to go to complicated theory of resonances to do so. And so again, values is when they coincide. And I would say that there's a huge activity in this area right now and in the last 20, 15 years. So there's a list of people who worked on it extensively. Avila, Avran, Belisar, Bourgain, Damanik, Eliasson, Froelich, Goldstein, Michel Herman, Lana Zhytomyrskaya, Krikorian, Last, Puig, Schlag, Spencer, Simon, everybody. The results we discussed above were perturbative and concerned with two different asymptotic regimes, weak and strong potentials. A big progress was achieved in developing the global theory, studying the whole range of parameters lambda. So not only large lambda and small lambda, but the whole range. For particular Hamiltonians, in particular, it became possible to study the transition from absolute continuous spectra corresponding to small lambda to pure point large lambda. The best studied is the case of almost Mathieu operator, for which almost a complete spectral picture is understood by now. And I'm happy to say that former Sinai student Lana Zhytomyrskaya, she worked all her life on this problem, and she was very instrumental. She made an outstanding contribution to this program. And very recently, I must say that Arthur Avila developed a global theory for general smooth potential, not for cosine, which was done before, but for general potential, which much harder. The theory is too complex to formulate the results. Okay, now I want to say that from physics point of view, and we're discussing mathematics and physics, what does it mean? It's transition from extended ground state eigenfunctions of Bloch spectrum to localized eigenfunctions of Anderson. What it means is that when they extend it, electrons can go freely through the material. So this is metallic state when you have electric conductivity. And when you have localized eigenfunction, it's insulated state. Electricity is not going through the material. So it's transition from conducting to insulating state. And now about almost Mathieu operator, what is known. So that is for this particular potential. So if lambda, and lambda is this parameter in front of the potential, between 0 and 2, the spectrum is purely absolute continuous for all alpha and theta. Even if alpha is rational, we know it's pure absolute continuous. Now, when lambda is equal to 2, the spectrum is almost surely pure singular continuous. Almost surely means that for all irrational alpha, there is a countable set of theta, which possibly exceptional. Conjecturally, they are not exceptional. Conjecture is that for all values, surely, not almost surely, there is a singular continuous spectrum. It's not proved yet. So, but with just except of countable set of phases theta, the result is known. And then when lambda is greater, the spectrum is pure point spectrum almost surely. Now this is known that almost surely cannot be made surely, because it is known that exceptions do exist. There are exceptional alpha and theta for which spectrum is not pure point. So I'm done here. I don't think I have much time to discuss Sinai's random walk, and it just was confirmed by a chairperson. But I would just finish by showing one picture. Well, it's, I would say that what Sinai proved is that in this particular case, the random walk behaved like not square root of n, like normal random walk behave, but like logarithm square n. It's basically stuck. It's not moving much, and that was particular case in very natural setting. So unfortunately, I don't have time to discuss it in details. I want to point just one picture. I'm not the author of this picture. This picture was prepared when Sinai was 75 by a group of his students, former students, admirers, colleagues, friends. And obviously, you can see that this is Moses, and this is tablets. It's not a paper, it's a tablet, this one, where 10 commandments are written. It looks like 6 commandments rather than 10, but still this is coming from where? It's coming where else, like Sinai said yesterday, from Sinai, right? And those are commandments. And you know, famously, Moses, when he took people of Israel from Egypt, he told them that they have to have random walks in Sinai desert for 40 years. And they had this random walks in desert for 40 years without being able to get to their goal. And I actually met for the first time with Sinai in 74, except I think it was in May. So it's exactly 40 years now. And so it was 40 years of random walks, and very enjoyable random walks, under guidance of these commandments and leadership of Sinai. And it was a very exciting journey. And I was an undergraduate student, and I was a graduate student, and then we were colleagues in Landau Institute, and then friends. And I want this journey to continue beyond 40 years. Thank you.